be inclined to say, this is not intellectually satisfying. I mean, there are so many ontological problems here. It's a dead-out feint. And so the difficulty then we have to handle, this is not a serious hypothesis. First of all, there's absolutely no ontological ground for such an anticipatory procedure or force or power or cognition or information packet to come out, because all of them are denied the moment that they come with sort of a supernatural emphasis. So, of course, we go flying back to the backward time causation things so that we can all of a sudden try and justify how the future of intelligent life is suddenly going to affect the past life. And I don't have to tell you that going backward in time has a lot of cosmological paradoxes. If I have my little spaceship out here and I decide I'm going to shoot a booby-trap bomb back in time, which now I can go back in time, right? And we get now, what's the name of that movie with Arnold Schwarzenegger? Anyway, right? You're going to go backwards in time. I shoot the bomb. Boom! I blow up the spaceship that shot the spaceship in the future. How'd you do that? Well, wait a minute. Just a minute. How did it exist anyway if it hadn't existed because it's still the future? Do you really mean the future? What I think of the future by the future? Or do you kind of mean that everything is coexisting? If everything is coexisting, including future events of the spaceship, then I'd like to know just how it's coexisted simultaneously with the other thing. Is it kind of like a divine intelligence? Nope, but there's no divine intelligence. So don't put that in there because you denied that hypothesis originally. In other words, the very denial of the supernatural intelligence that could hold together coincidentally past, present, and future events sufficient so that the future as a non-existent existent could actually draw the past to itself, the very denial of that makes the strong anthropic hypothesis pretty dubious. At the very least, not intellectually satisfying. So the weak anthropic principle came in its wake. And the weak anthropic principle goes like, and Steve gave it a little bit of a introduction to it when he was talking about the so-called Planck era, quantum cosmological era, that 10 to the minus 42nd of a second, where typically, supposedly, where the universe could have given rise to an infinite number of possible universes. Now, I'm going to state right now that there are a lot of reasons for not believing this, not the least of which is a problem in general relativity itself, which would require that if you do not reduce the space-time continuum to a so-called singularity or to a point, and you round it out, you're going to actually have in that rounded out universe that doesn't reduce to a point, you're going to have time emerge from space. And of course, get it? Time emerge from space? An emergence is always a before and an after. In other words, an emergence is not there, then there. So what you basically have is a fundamental paradox, because remember, if we mean anything by time, it has to be the conditioning of existence by some non-contemporaneous magnitude. If time's anything, it's non-contemporaneity. So somehow, you're going to have a before and an after. No, you're going to have the whole of non-contemporaneity, time, emerging, a before and an after, a non-contemporaneous event. You're going to have time emerging before there was time, which required time in order to emerge. We call that a paradox. And it is quite irresolvable. You need time. You need a non-contemporaneous magnitude or a non-contemporaneous conditioning of existence in order for anything to emerge, including, supposedly, time from space. These kinds of paradoxes have not been answered. But I don't want the whole argument to hinge on my ontology. Let us grant, for just one moment, let us grant that the universe really did emerge out of this so-called Planck era in which there was literally an infinite number of universes. And you could, along with Stephen Hawking, you could indicate that all the universes somehow existed in some way simultaneously in that moment, or that they were merely a superposition and they were existing kind of potentially and ours luckily popped out, or any other hypothesis you want. Attribute any ontological status to the universes in the Planck era. And what I would suggest to you is you cannot get out of the paradox, the vexing paradoxical nature of the anthropic principle without faith. You're not going to get out of it. What do I mean by this faith once again? Either you're going to believe that a supernatural designer gave the constants, cosmological constants, the values that they had, and don't confuse that with another cosmological constant that was just being talked about that has a positive value, giving rise to inflationary universe hypotheses, which will explain the so-called galactic nebulae phenomena that we just heard about. But cosmic, then, call them cosmic constants, that we have. So the key thing right now is, what's this faith? Either you have faith, you believe, reasonably and responsibly believe, that this was done by an intelligence, or you reasonably and responsibly believe, quote unquote, that a virtual infinity to one occurred by pure chance. But belief you have. One way or another, you cannot avoid it. Let's take a look at it for just a moment. What are the conditions for the complexity necessary for a life form, a so-called anthropic universe? What are the conditions necessary for that to develop in any possible universe? I will use our universe as an illustration, but what are the ones you'd need in any possible universe? Number one, you're going to need some kind of units of complexity. Units. That's right. Complexes are formed from units which are smaller or less complex than the complex out of which the units out of which the complexes are formed. So in other words, you're going to need some units that are more fundamental for the complexes to be formed from. Okay. Now, in our universe, we call this the unit mass of a proton, the unit mass of a neutron, the unit mass of an electron. And we also call it the unit charge of a proton-electron. And we also call it the unit, or we call it the conversion of mass into energy, which is, of course, c squared is equal to E over m. So that would be the conversion ratio. Okay. Now, these five things, they are kind of our units, as it were. They're kind of like the fundamental grounds that get organized into complex. But you could, in any possible universe, you could have all kinds of things with different unit masses, different unit charges. Heck, they don't even have to resemble electrons or protons, but you will have to have some units. And here's the other thing you're going to need about those units. Those units are going to have to be repeatable. That is to say, they're going to have to last for a while. You can't have them switching around on you. Otherwise, you're not just going to not get evolution, right? I mean, you got to have those units kind of being consistent and repeatable, right? Otherwise, right, nothing's going to build on anything else. So you're not going to have the universe evolving out of its plasma state into the next state and so forth and so on, right? It's just going to, right, it'll be bizarre, and then the next minute even bizarre, then the next minute quick, and right, right? You need them to be consistent, and you need them to be repeatable. So in other words, you need your units, you need them around for quite some time. There's a little, I put those units on a view foil there, if you know, and it just gives you the unit charge of the electron, proton, neutron, so forth. So you can see this is what's in our universe, but you don't have to have them. In any possible universe, you'll need units which are consistent and repeatable. The second thing you're going to need for a complex life form in any possible universe is you're going to need those units of interaction. You're going to need consistent and repeatable relations of interaction. Or sometimes we call them laws of interaction. So in other words, we need things that continue to, organize the protons and electrons according to certain kinds of principles or certain kinds of laws to keep them ordered. Remember, if you don't keep them ordered, they're not going to be around very long. You're not going to be able to build on them in complexes. You need to build on them. You're not going to have them evolving from one stage to another stage, right, so that they can get higher and higher levels of complexity, right? You're going to need some evolution. You're going to need some genesis. You're going to need some build-on time, right? And you can't have your units of measurement relating in one way 1 minute and then relating in another way another minute, because all you're going to get is a chaotic universe if you have that. So you really need consistent and repeatable laws or determinations of the ways in which these units interact. And in our universe, as you can see from the next viewfoil, we have 5 basic ways in which our units interact. And you can see the so-called Hamilton mechanical interactions, right? The equations for describing the Hamiltonian equations describing mechanical interactions. We also have the Boltzmann equations, which are describing statistical mechanical interactions. We also have the Maxwell equations, which describe electromagnetic interactions. We also have the Schrödinger equations, which are quantum mechanical interactions. And finally, of course, we have the Einstein fundamental equation, which is going to describe the space-time parameters and the conditions of space-time in our universe, which is so-called tensor equations. Now, these 5 are really consistent, and we really need them to be consistent. And if you start moving them around, the universe can't build up its higher levels of complexes. Luckily, we had consistent, repeatable, deterministic relatability among our various units of interaction, and we're safe. We're safe. But it didn't have to be this way. You didn't have to have Boltzmann's equation. You didn't have to have Maxwell's equation. Right? This just happens to be our universe. I mean, it could have been. But in any possible universe, you're going to have those consistent, repeatable, interrelated laws or determinants of the interaction among the units of interaction. You're going to have that. Point number 3. The third ingredient you're going to need is some consistent, repeatable constants for those equations. Now, constants are like real numbers. They're not like variables, as most of you probably know. Constants are real numbers, but the real numbers they describe the real relation, the hard, concrete relation between the units of interaction according to those equations, according to those determinate, consistent, repeatable equations or determinants of interaction in our universe. You need real constants. But it's not just the constants that you need. In order to have an anthropic universe, you need more than the constants. You need the constants to have the precise right values that correspond to your units of interaction and your equations or laws of interaction. In other words, your units of interaction and your laws of interaction are demanding that the constants have a very precise, narrow range in order to give rise to a life form. We don't want any black holes out there. That's really hard on life. It's really hard on complexity. We don't want any too immediate dispersions out there. Really hard on life if atomic nuclei can't get together in some way, form the whole periodic table of elements. It's really hard, and you don't need carbon-based life, right? But you're going to need something that functions like carbon in any possible universe. You're going to need it there. So here is the principle to think about from the very beginning. In any possible universe X, given consistent, repeatable units of interaction and consistent, repeatable laws of interaction, the constants that pertain to concretizing those laws of interaction in the world will have to fall within an extremely narrow range in order for an anthropic universe, a universe that will give rise